Hi friends, welcome to my channel. Let's have a look at today's daily challenge problem. That is problem 1578, minimum time to make rope colorful. In this video, we are going to share two formats of solutions. So one is a linear scan, and the second is a stack simulation. So the idea actually for this problem is very simple. So for each consecutive colors with length greater than 1, so we leave the 1 corresponding to maximum time or cost. So in our implementations, actually we changed the function signature a little bit. So we changed the colors to be S, and we changed needed time to be cost. So this is just for the ease of writing. So before we write code, let's first look at the statement to digest the problem requirement. So we are given a two arrays. One is called colors, and the other is called needed time. So we want the rope to be colorful. In other words, we want that no two consecutive balloons have the same color, right? So we want to return the minimum time we need to make the rope colorful. So as we using the idea here, actually let's examine example 1. So in example 1, here is a two consecutive colors, right? So their cost correspond are 3 and 4. So we're going to leave 4, and so the time needed with 3, right? So that's example 1. For the generic case, if we have the last 3 balloons are all blue, so for example, their cost is 3, 4, 5 respectively, and the largest would be 5. Then the cost will be 3 plus 4. That will be 7, right? So notice again, so if we are talking about if the last 3 balloons are all the same color, that is blue, and the cost are 3, 4, 5. In that case, the cost will be 3 plus 4, 7. And in the problem or in the example here, so there are only 2 consecutive colors. So the output is 3, as in example 1. So with example 2 actually is special, right? So in this case, so no consecutive colors of length greater than 1, so the cost is 0. So in example 3, so here are 2 pieces of consecutive colors with length strictly larger than 1. So in the first 2, actually we should leave the second one, so with a cost 1, right? So in the last 2, we're going to leave the 1 corresponding to index -2, and then we use another 1 as a cost, that is 1 plus 1, that is 2. So this is actually example 3. So with the examples covered, let's look at the additional constraints or assumptions. First, so consistency. So colors and needed time are the same length, of the same length, and they are bounded above by 10 to the power 5. So this second constraint actually defines the problem size, and the third one is on the range of elements in the needed time. So here colors contains only lowercase English letters, so actually that's not very essential for this problem. So with that said, let's look at the code. So for writing the code, I'm going to first write a solution based on linear scan, and then we're going to write a solution using the stack simulation. So let's first look at the linear scan solution. So in other words, we just need to a linear scan of single path, so linear scan. So in this case, actually we can write this code very short, but for readability or for the ease of understanding, so we are going to write in some detail. So first, I'm going to track the length of this S. So notice that S corresponds to colors, and the cost corresponds to needed time. So here, length is S. So we're going to initialize a result variable, whose final state is what we want to return. And then we're going to initialize a maximum time. So that's going to be cost 0. So also we're going to use a full time. So that's going to be cost 0, right? So and the size, we're going to initialized to be 1, and the color will be S0. So here the meaning of these variables are the following. So if we have a certain sets of same colors, so we're going to record the maximum time among these same colors, and also we want to record the full time, in other words the sum of the times, and we want to record the size. So actually the time needed for make this consecutive piece of color to be left just 1 or make it colorful, the time needed will be the full time minus the max time. In other words, for this consecutive piece, we leave the balloon corresponding to the largest time, and then we sum the remaining time. That part is our cost needed. So this is the preparation. So actually we do not need this if we just solve this problem itself. But for the explanation, we want to make it more convenient to understand, or easier to understand. So with that said, let's write the for loop. So here we are going to start from index 1 now, right? Because we have used the index 0 information here. So for I in range, so 1 to n. So first we're going to get the current color. So the current color is nothing but SI, right? And then we want to compare the current color with the previous color. So of course, two cases. If current color equals the previous color, that is equals color, then in this case, so we're going to increase the size by 1, right? This is for sure. And the color is not updated, but the full time should be updated. Full time is incremented by this cost I, and the maximum time should be updated. Max of the previous state and the current cost or time. And then so that's it. So we updated these 3 pieces of information. So in the other case, so in other words, we meet a new color, then we're going to check so if the previous size is 1 or not. So actually, no matter it's 1 or not, so we can do this. Result increment by, let's see, by full time minus max time. So in the case that the size is 1, actually full time minus max time is nothing but 0, right? Because full time just consists of one single time, that is max time. So in this case, because the color has changed, so we're going to reset the color, so to be current color. And also we are going to reset the max time to be cost I, and the total time or full time will also be cost I. Then the size will be reset to be 1. So this is the other case. So notice that in this way of writing, so if we arrive at index n-1, so we shouldn't miss the last check. So if I equals n-1. So in this case, so actually we want to check if size does not equal to 1. So actually we can increment the result by full time minus max time, right? So actually we do not need this check. Actually we can directly do this. The reason is that if the size is indeed 1, so this will increment 0, right? So with that said, we are ready to do the check, do the return. So we're going to return the state of the result variable. So with that done, let's do a check first. Yeah, it passes a test case. So now let's look at the generic case. Yeah, it passes all the generic cases. So before we write the second format, let's make a comment on this. So this is a linear algorithm or linear solution, and for sure this way of writing is for presentation purpose. So we can actually greatly simplify the solution of the code format. So but that's not our purpose. So let's copy this function signature and then let's do another format just for a simulation purpose. So here I'm going to use a stack simulation, right? So for this, I'm going to reset a variable called result as to be 0. So this result state is what we're going to return, and then we're going to initialize a stack. So the stack will contains s0 and cost0. So then we are going to do the traversal. Actually, this I would regard as a translation or another representation of the first solution format. Then we are going to iterate from index 1 up to the end, right? Then we are going to check the current color and the previous color. So if si equals the previous color, that is stack -1 and 0, and then we're going to consider which one is larger, right? So if which one corresponds to a larger cost? If cost I, the current cost, is greater than the stack -1 and 1. So in this case, we're going to maintain this cost I and add this one to our result, right? So our result will be added, will be incremented by this stack -1 and 1. Then we're going to pop that stack, and then we're going to append the current information to the stack. So that is si and cost I, right? So this actually, the effect of this is actually to maintain the same color corresponding to the largest time or cost. So if actually the color is not the same, so in this case, so we're going to so because in this case cost I will be less than or equal to the height element, so we're going to increment the result by the current cost, so cost I, right? In other words, we choose the larger one as soon as possible. And then this is the case. Otherwise, so if the colors are different, then we're going to just put this new information into stack. So the si and cost I. So that's it, I guess. Then we're going to return the result state. So I would say this solution format is no difference than the first one, but the difference might be in the code formats. So with that said, we have changed the function signature. So now let's do a check. So n is not defined. Oh, sorry. So let's first write this n to be length s or cost. It does not matter. So here actually we can directly change this n to be the length of s. So let's do the check again. Yeah, it passes a special case. Now let's do the generic case check. Yeah, it passes all the generic cases. So I guess that's about it for this problem. So in this video, we shared two formats of solutions. So the first format actually is based on a for loop, in other words, a linear scan. And the second solution format is based on stack simulation. I would say the two formats of solution actually corresponds to the same idea. And essentially, they are the same solution. So with that said, I guess that's about it. Thank you.